Hello everyone, thank you very much for coming. So I'm very proud to introduce you guys Qianqian Lin. He did his PhD at the Queensland University. After that he was a postdoc at Oxford, and then he went to China to become a professor at the Wuhan University, where he has like a little research group, and since 6 years he is leading that group. And he's very active in research output, which you will see in the presentation. I think so far you have over 110 publications, is that correct?
Yes.
Yes. And so I'm very much looking forward to his presentation, because we know each other already for a longer time. We both have the passion for characterization equipment. So please take it away. Thank you so much.
Thank you. Thank you. Thanks for Hannah's introduction, and thank you for the kind invitation. And it's my honor to be here to introduce my recent work. And my group is mainly working on characterization and the devices of next generation solution processed semiconductors. So my main working target or my materials is organics, chalcogenides, and hybrid perovskites. These materials can all be solution processed with very low-cost equipments, but we are not actually making materials by ourselves. We got the materials from collaborators, from the company, and we are mainly working on the properties. So when we get materials, for us it looks like a black box. We don't know anything about the materials, so we just know the color, it's solid, it's powder or liquid. So the first thing for us to do is to test the optical or electrical properties. So we do look at the optical constants, the dielectric constants, the conductivity, mobility of the, if it is a semiconductor, and the trap density or the binding energy of excitons if they are excitonic. And after measuring so many physical parameters or properties, we then move on the devices. So we'll test the optoelectronic processes within the device. So we use operational devices and tested the charge carrier generation, and we will look how much or how many is the generation yield after the carriers, electron and holes generated, and we will look how the carriers diffuse, drift within the active layer. Then during the charge transport, the carriers may recombine with each other. Holes will recombine with electrons and get emitted photons, or it can be trapped by the trap states. Then we will get efficiency losses. After the carriers reaching the electrodes, the carriers can also be hindered by interlayers or barriers, and we will look at the charge extraction. And for light emitting devices, we also look at the charge injection processes. So all the physical processes actually limited the real performance of all devices. So we also do device work. We are optimizing the efficiency of solar cells. We are working on photodetectors and also LEDs, but we are optimizing it with a way of looking at or optimizing, designing better charge transport processes based on the understanding of these parameters. So this is a general view of our research. So my work is focusing more on characterizations, or it's more or less dependent on the characterizations. So there are so many parameters. So we can do almost all of them, but today I'm just going to have a look more carefully on the mobility, which is a key property of semiconductors. So how do we measure the value or the mobility of a semiconductor? So we can get from the textbook. So we use Hall effect. Classically, we use it for silicon, for very conductive semiconductors. But Hall effect do have problems for solution processed materials. So for organics, for perovskites, the conductivity is so low, and the mobility is more than maybe 6-7 orders of magnitude lower than silicon. So it's very hard for us to use Hall effect to measure the mobility of perovskites and organics. So we have to develop new techniques to measure mobility. So in early years, so people use time of flight. So this is a very typical transient measurement to measure mobility. So how do we measure the velocity of people or our bicycle? So if we walk from home to our office to the university, then we know the distance, and we know how we can count how much time we need for the walking, and we can easily calculate our velocity. So how can we measure the velocity or the mobility of charge carriers for electrons? So we use time of flight. So we deposit 2 electrodes on each side of the semiconductor of the active layer, and one side is transparent, so we can photo-excite the semiconductor. So we give a laser pulse with very short time, we excite the semiconductor and get a lot of carriers on the interfaces. And the carriers could be drifted under the bias voltage, and we can easily measure the thickness of the active layer, and we can also record how much time it needs for the carriers to reach on the other counter electrode. And we know the distance and the time, we can get the velocity of electrons. And if we also divided the electric field, then we get the mobility. This is the basic definition of mobility, and we can measure it if we have a very fast oscilloscope. So ideally, for TOF measurement, we can get ideal TOF like this. If all the carriers reach the counter electrodes, we can get a transient time. This is very ideal. At least I have not seen such transients. And this is more real or good TOF. So if you get a TOF like this, it's good. You can get kind of a kink from here. So the kink is almost close to the ideal transient time, and you also have kind of deviation from the kink because the charge transport is very dispersive. First, we photo-generated the carriers. It follows the Beer lambda law. So some photons could be absorbed just in front of the material, or it's very close to the electrodes. Or some photons can penetrate much deeper, and it follows the Beer lambda law, right? So some carriers can be generated much deeper inside the active layer. So if this electrons goes to the counter electrode, it has much shorter distance. That's why we get a dispersive transient curve. This is the first thing. And the second, some carriers may go directly to the counter electrode, but some carriers could be scattered by the nucleus, by the green boundaries, and they may go not very straight, and the distance could be extended. That's why we can get another reason for the dispersive curve. But anyway, this is also a good TOF, but for some materials we do have very bad TOF, then we do not see any kink from the curve or the decay. So we cannot get very valid or reliable transient time from the TOF measurement. That's the drawback of this measurement. And TOF measurement also very dependent on the field or the bias voltage. And normally, a high bias voltage is required for the TOF measurement. It may cause film degradation for some organic materials or perovskites, because on the high bias voltage, perovskites can have ion migration, and it will affect the real measurements. So this method works, but most of them work for really good, like perovskite single crystals for thick films, but not for very thin or with very dispersive charge transport. Then people later on developed new methods to overcome these drawbacks. So then this is another method called charge extraction by linear increasing voltage, or shortly we can call it photo-CELIV. For photo-CELIV, we also use a laser pulse to excite the semiconductor, and we can get charge generation, but we extract the carriers not immediately with a constant bias. We increase the constants. We constantly increase the bias voltage linearly. Then we can get a displacement current like a rectangle here. Then we get extra carriers just from the photoexcitation. So the blue area here can get from the photoexcitation, and the underneath is the displacement current. And from this, if we know how much photons we use for the photo generation, and we know how many carriers we got from the transient, because this is the current density. If we integrate with time, we get the number of carriers. So if you know the carriers we get collected, and if we know the photo generation, then we know the quantum yield of our device or semiconductor. This is the first we can get the yield or the EQE, quantum efficiency. So, and the second thing is we can get a very dispersive peak, and we know the peak here is the average or mean transient time for the carriers, and some carriers reach the contact electrodes earlier, and some get later. That's why we get a dispersive charge collection. So for this method, it rules out the displacement current, so we do not have any effect from the RC decay, and we can get it clearly from current transient. But for this method, we also have the problem of dispersion of photo generation, and we get the mobility. It is a mixed mobility, so we cannot distinguish which one is hole and which one is electron. So it's also photo generation dependent, and for some devices, for highly recombined systems, the current transient are not so clear. It also affects the method a little bit. So we want to further improve the CELIV method. This method called CELIV, developed by Adlan and other colleagues. So use this method, we insert an insulator, magnesium fluoride, between the ITO electrode and active layer. So the thin insulator is just like a capacitor which can store carriers. So in this method, we also removed the photo excitation. We inject carriers with like forward bias, and we inject carriers constantly here for a certain of time. Then the carriers may accumulate just on the surface of the capacitor. So we get kind of constant inject generation, and we get all the carriers just on the surface. Then we start to extract the carriers with reverse bias. So we immediately change the sign of bias, and we linearly increase the bias voltage. We can get also the transient, and from this way we reduce the dispersion of photo generation. So we want to improve the method to get more or less dispersive transient from this CELIV. And this method also can tune the work function of metal electrodes. So if we use aluminum, we normally inject electrons, and if we use gold with high work function, we can inject holes. So from this method, we can distinguish hole and electron mobilities. But we still have kind of dispersive transients because all carriers can get scattered. For these three methods we use are all transient measurements, so they are time resolved. We do need kind of faster oscilloscope, and then we are thinking how can we measure the mobility without oscilloscope? So if we cannot measure the transient time, how can we know the mobility? There are methods literaturely. So the first one I want to say is the space charge limited current method. It has been used a lot in publication, but the problem is there are some very tricky things in this method. So at low, we can look at it carefully for this method. At low bias voltage, so the current follows, or the JV curves follows the Ohm's law. So it increases linearly with voltage. So everyone knows it from school. And if we increase the bias voltage, we can inject a lot of carriers. If the inject carrier density is much higher than the intrinsic carrier density within the active layer, then the carrier density changes. It immediately increases the conductivity of the active layer. That's why the Ohm's law didn't work for the high injection region, and we got kind of SLC region. And from the steady state measurement, we can get kind of IV or JV curves. And from the JV curves, we got two regions, and from these regions, we can extract the trap density and also the mobility as well, because we know the charge numbers Q is equal to the product of capacitance and voltage. So we know the Q, and if we know the current density, then we can extract the transient time indirectly from Q divided by J. Then we know the transient time. If you know the transient time and the distance, then you can also calculate the mobility. So this is a very good steady state method, but for real measurements, it has problem. And for real measurement, we normally use both like electron and hole devices, because we can selectively fabricate devices with low work function or with very high work function. Here's arrow, so here should be gold. So we can separately measure electron and holes, but if we use many interlayers, it may affect the measurement. So for real measurements, this is not. So for ideal measurements, we should measure the resistance of the whole device. And we got the JV curves, and we can extract the mobility. But for real measurements, we always have like series resistance, we have ohmic contact problem, and it can also be affected by the trap states. And this is real measurement. It's also good because the resistance of active layer is much larger than the contacts. So it's reliable. But for some measurements, for some materials, they are very thin. For example, perovskite thin films, if you have like 300, 500 nanometer thin, and it's very conductive or it's slightly doped materials, then the resistance will be very small of the active layer. If you have much larger interlayer or larger resistance of interlayers, then you didn't get anything. You won't get reliable like SLC results from these measurements. So this is not ideal. How can we measure mobility further? So we do light intensity dependent photocurrent measurements. So this is another steady state measurement. So we just use CW laser to excitate our devices and we get photocurrent. So under low photogeneration regime, the current normally goes linearly with photogeneration. So it's linear, but under very high illumination, the photocurrent may deviate from the linearity because more carriers get recombined. So the recombination region is much higher than here's a linear region. From the kink, we can also get the transient time because if the carriers can move not fast enough, then they can meet each other and get recombined. If they can move very fast, then the recombination rate can be lower. So from the kink, we can also determine the slower mobility of the semiconductor. So if you, I won't say more about this technique, but this technique do tell us something about charge transport, and we can determine the slower mobility. And this is very easy to measure. So we just need a steady state like CW laser, and we can tune the intensity and get photocurrent. We can easily extract the mobility, and we can also have a look at the charge recombination. We can know how many carriers get recombined from this measurement. So if it deviates more, then it means it has more recombination. It deviates slightly, it has less recombination. So this can also give us the quantum yield at different light intensity. So these are all electron measurement. Recently, we are also working on some spectroscopy based on the time-resolved technique. So the first thing, or the first technique I want to talk about is the time-resolved photoluminescence. So TRPL is widely used in the field of perovskite community. We can use a few methods or technique to record the TRPL. So the TCS-PC one is the single photo counting one is the most common one we use, and I also use the intensified CCD. So it is fast and it can also record the spectra versus time. So we can get like almost a PL spectra at each 4 nanoseconds. And we can get more information from the ICCD. Then we can also have street camera. If you have, you will get much faster than ICCD. You also get the spectra, but it's more expensive. So if you want to look at a very short region, then you can go to femtosecond photoluminescence upconversion. So the femtosecond PL upconversion, one can get the PL lifetime in the femtosecond or picosecond region. So all the methods, all the techniques we can get is that time-resolved PL. So the decay is like this. So if we can tune the excitation or the light intensity, we can get different decays because at under high light intensity, the carriers recombine quickly. Then we can fit the different decays and we can extract the recombination constants. So for this monomolecular recombination rate, bimolecular recombination rate, and order. So we can get this recombination information from a set of light intensity dependent TRPL. We can also extract the carrier diffusion from the bilayer measurements. So if you put interlayers in front of some active layer, and you excite the films, but the bilayer you can get charge diffusion from this from the quenching process. So you can also extract the diffusion constants or the diffusion length from these measurements. It has been done a lot for TRPL, but this technique also has some problems. It normally gives you the minority of the semiconductor. So if you have an intrinsic semiconductor, it doesn't matter. It gives you a kind of lifetime. But if you have kind of slightly doped semiconductor, it will give you more direct information about the minor carriers. Because if you have like 50 electrons and you have 100 holes, then 50 electrons may combine with 50 holes and get emitted photons. All your measured signal is the emitted photons. So how about the other 50 holes? You cannot get direct information from TRPL. Another drawback is TRPL can be used for most of the direct bandgap semiconductors because most of them are emissive. For indirect bandgap materials like silicon or some highly doped semiconductors, they are all with high trap density. These materials are not so emissive and you cannot easily get a TRPL signal. This is the drawback of this technique. That's why we want to develop new methods to look at the charge carrier dynamics. Here I want to introduce the time-resolved microwave conductivity measurement. We can say it TRMC. For TRMC measurement, we also use for the same mechanism for optical-pumped terahertz-probe spectroscopy. So the mechanism is the same. So we can probe the semiconductor with terahertz or microwave. And if you look at the intrinsic semiconductor, they have very high transparency. So if we record the transmittance versus time, it's steady state. If you excite the semiconductor with a laser pulse, you can generate photogenetic carriers. So it's electron holes everywhere within the semiconductor. All the carriers, the electrons, will not stay there. They will move, they will diffuse, they will move, and if the carriers move, they will absorb, and they have energy, and they will absorb energy. And the energy of terahertz or microwave are similar to the energy of electrons, the moving of electrons. So they are similar. So the moving of electrons holes will absorb or reduce the transmittance of the microwave. So the transmittance reduced immediately because the laser pulse is very short, normally around 1 nanosecond or less than a few nanoseconds. So we just get a drop of the transmittance. But the carriers cannot live long. They will recombine. So electrons meet holes, they get emitted, so we get radiative recombination. And the carriers can also be trapped, and it can be lost with as heat. So the carriers will recombine radiatively or non-radiatively. Finally, the carriers will disappear, and we can get a recover of the transmittance. So if we can record the transients of this transmittance or reflectance, then we can get the time-resolved microwave conductivity or terahertz. And the decay mainly dependent on the recombination processes. And for this measurement, we get all the information of radiative and non-radiative sites. So the recombination is dependent on all the carriers. So if it is intrinsic semiconductor, this decay is more or less like overlap well with TRPL. But for some materials like with heavily doped or with a lot of trap states, the decay will be quite different because the majority carriers will dominate the decay, not like the minor carriers. So this is the mechanism of TRMC. So we also use the same thing for the optical-pump terahertz-probe spectroscopy. And we can, from the transients, we also get the recombination constants and the diffusion length, mobility, and so on. And this is a difference between the TRMC and the OPTP. Normally, terahertz have higher energy, and it have like a smaller probing length. Normally, it's around a few nanometer or less than 10 nanometer. It's around here. But for the lower energy microwaves, it has much longer probing length. So the probing length can reach, if the mobility is high, the probing length could be larger. It could reach around 100 nanometer. So this value is around the grain scale of perovskite crystals. So if we have like a larger probing length, it can have the information of charge interaction with the grain boundaries. So for these two measurements, OPTP or terahertz spectroscopy normally give you a higher number, and the TRMC could consider the boundaries and can get more information or get slower, lower mobility because of the boundaries. So this is the setup of our TRMC measurement. We have like photo excitation with like nanosecond laser. We can also use femto laser, and we can tune the wavelength and the light intensity easily from here. And here's the microwave cavity. So we put samples within the micro cavity, and we can increase the sensitivity quite a lot. And for TRMC measurement, the sensitivity is much higher than the terahertz normally. And we can also have microwave detection system here. So from this setup, we can record a kind of 2D spectra, time-resolved spectra of the TRMC measurement, and we can look carefully about the 2D spectra. If we go through this line and horizontally, we can know here is a photo excitation, and the transmittance or the reflectance, the microwave signal changed immediately from this point, and it has kind of decay back. So you can put a sign here, and we can change the polarity of the signal. So you can get a kind of decay from the horizontal line, and if you look at the vertically, you look at the spectra here. So you look vertically, you can get the spectra in dark and under illumination. So it's different. So the spectra also changed a lot. From the change of spectra, we can get the information of traps. And because under the photo excitation, so we look at the state in dark and under illumination. So it can have kind of photoconductive effects. So the amplitude changed under illumination. And we can also have photodielectric effects. So the phase shifted, but the amplitude didn't change. Normally we have the mixed effect, so we have both change of phase and also amplitude. This is a typical TRMC measurement we recorded in our lab. So we can record the spectra versus time, and we can get the amplitude versus time as well. So from this time-resolved measurement, we can analyze the mobility and carrier recombination processes. And we can also fit the decays at different under different intensity. And if you have different decays, and you can fit with the continuum equations, and you can easily get the density of trap states. So this is a kind of fitting of the decays. We can measure a lot of materials based on the TRMC methods. So recently we measured the typical organic materials like P3HT. We can also measure chalcogenide. Mainly we are working on bismuth sulfides, antimony sulfides, or silver bismuth sulfides. It works well. We can also use these methods for commercial semiconductors like gallium arsenide, indium phosphide, and it works much better than solution process materials because the signal or the mobility are a few orders of magnitude higher. So the signal is much more stronger. We can also use it for wide bandgap semiconductors like gallium nitride. So it works. And we use this method for a lot of perovskite research. So we do not make devices too much in my group. So we collaborate with a lot of groups in China or overseas, and we recently helped them publish some results for perovskites, both for tin lead perovskites and also some 2D perovskites. So it also works for the perovskite community very well. And if we combine optical pump terahertz-probe spectroscopy and microwave conductivity, we can get a more we get more information from the time-resolved case, because normally terahertz spectroscopy can record the decay in the picosecond region. It's much faster. And we can also record the slower decays from TRMC. If you combine, if you combine these two decays, you can get a clear or more information from these measurements. So we did it for bismuth sulfide recently. And if I want to summarize these two classes of measurements, normally electrical probes, so like CELIV or TOF, we normally have underestimated mobility because you have the contacts, you have grain boundaries, the carriers have to go through the devices, and normally the value are slowed down. And if you use optical probes, normally you will overestimate the mobility because the photons normally interact with the semiconductor within a very short probing length for the terahertz. So if you use optical methods, sometimes you will get a little bit higher mobility or overestimate the mobility of multi-crystalline films because you do not consider too much about the boundaries. So this is a comparison of these two methods. And for the transients, we also analyze trap states. So for different perovskites, we measure the different spectra, and we get different decays from the phase and also the amplitude. So the phase is more sensitive to the traps, and the amplitude is more sensitive to the moving of carriers. So it's the mobility. So the decays could be different. And if you fit the spectra of terahertz and microwave, if you have a lot of sources, if you can change the microwave energy and to terahertz, you can get a broader spectra. Yes, then you can use the Druck method to fit the curves. You can get more information. So this improved Druck standard model. You can fit the curves, and if you have traps, so this model is proposed by Seki, and the traps will also affect the spectra of the microwaves a lot. So if you look at the real and imaginary part of the conductivity, you can get the information of the levels of trap states. So from the decays, we get the numbers, but from the spectra, we can get the energy level. So it's different. So we can get the energy level and also the effective mass of the carriers. And this is how the traps affect the charge transport. I will take the photo, for example, if you have a car, go on the road, and if you have some traps on the road, cars can be trapped, right? So if the holes are very deep, then the people or cars will just fall within the hole and can never get out. So it will slow down the speed of the charge transport. So but anyway, for TRMC measurement, we always get shallow traps because all the measured signal are mobile carriers. And you can also use steady state measurements for like PDS or sensitive EQE. You can get the tail of your absorption or the tail of your EQE. You can get the shallow traps as well. So we are working on more on the sensitive EQE recently. And we can also measure other methods to measure the dips or deep trap states. So for the deep trap states, you can never get the carriers out. So how can we measure the dip? So for old people, you can throw a stone to the trap, to the well, and to the traps, and we can count the time, how much time we need to hear the echo. So we can count 1, 2, 3, and if you know the time, you can probably know the depth of the hole or the trap, right? So similarly, we use time-resolved measurements. Here's time-resolved capacitance to measure the deep level trap states. So the deep level trap states are normally in the middle or normally lower than the Fermi level for electron or for N-type semiconductors. So if we can get some basic information from the semiconductor physics. So if you have P-type semiconductor and N-type semiconductor, you have different Fermi level. And if you combine these two materials together, you can have a p-n junction. So you will have kind of like bending, both for conducting band and valence band. And you will have a region called space charge region. It is highly resistant, and also its property is mainly dependent on the minor carriers. So you have a kind of space region with less carriers and is highly resistant. And from this junction, you can get the information of the carriers. And we can consider this region more or less like a capacitor. So the capacitor is dependent on the area and also the width. So this is the first equation we get from the textbook. And we can also, because we want to know the property of the carriers, so we have electron and holes for normal p-n junctions. So we can get both informations. So ideally, I want to get rid of holes or get rid of electrons, easily dope one side. So we have heavily doped p region. Then we reduce the width of the p region, and then we have then we measure the capacitance. It is mainly dependent on the n side. So we can say we get the property mainly for the n-type materials. So we normally use p plus n junction for real measurements. And here's another equation from textbook. We can have the width of the space charge region, and it depends on the carrier concentration. So the carrier concentration higher, then the width will reduce. This is the second equation we get. And the third thing is the bias dependent for p plus n junction. So this without bias, it has kind of bending. If you bias it with forward bus. Since you will inject carriers, right? You inject under forward bias, then you get higher carrier concentration, then you will reduce the width a lot. Then the band bending is not so much like this one. Then you have reverse bias, then the width of the region will be extended. Then you have sharper band bending. See, then we combine these two equations, you can get the bias dependent capacitance. If you change this equation a little bit, you can get the reciprocal of C square, and this number is linearly dependent on voltage, right? So from this measurement, we normally plot it like this, and from the steady state CV, we can get the carrier density, also built-in field from this measurement. This is a typical measurement from the equipment. We can get the steady CV. It has nothing to do with traps, and nothing. What will happen if the material has traps? So it depends on time, because the carriers can be trapped and re-emitted. So the emission rate is highly dependent on the depth of the trap states, and also the temperature. If you have higher temperature, it has more energy to escape from the trap states. So it depends on the temperature as well. So we have the emission rate dependent, a temperature-dependent emission rate, and the velocity is also dependent on temperature, and the density is also dependent on temperature. Finally, we can get kind of temperature-dependent emission rate. So keep in mind, it's dependent on time, and so the emission of the carrier is dependent on time and temperature. So we look at the transient of the capacitance measurements. So we also have the P plus N junction, and all the carriers will be trapped by the trap states because it's deep, so it can easily trap below. It is below the Fermi level. Here are all filled with carriers, but you have band bending in the space charge region, so the trap states will be higher than the Fermi level, and it cannot be filled within this region here. So if you look at steady state under reverse bias, the capacitance will be a constant. If you bias it with a positive bias, so if you give a positive pulse, and the band bending will be reduced, and the carriers will be injected, right? So the band bending reduced, and the energy level of traps will be lower than the Fermi level, and all trap states can be filled. And you have kind of slow changed capacitance from under the forward bias. And if you remove the forward bias immediately, you will get also a picture like this. So the carriers trapped by the trap states will not emit immediately. It takes time, and it's also dependent on temperature. So the carriers trapped by the trap states will go out to Fermi level slowly, and the capacitance we measured from the device is even lower than the initial value, because all the carriers are trapped by the trap states, and it is not moving. That's why we have lower carrier density for the region, and you will have a wider space charge region and a lower capacitance. Then slowly the carriers goes to Fermi level, and you will have kind of decay back to the initial value of capacitance. So these are two processes. One is called capture process to fill up the trap states, and the second step is to record the emission process of the trapped carriers. So if you can fit the curves, we can get the information of deep trap states. So we can inject carriers with forward bias, or you can also use a laser to optically inject carriers or change the space charge region as well. And you can modulate the width of the pulse or the amplitude of the pulse. You will get different transients, and you can get the saturation of the space charge region. So from the saturation, you can get the number of trap states, not the energy level. So here is the number of trap states, the density. And if you look at different transient capacitance at a different temperature, so this is a typical DLTS measurement, so you will get a different case. At low temperature, the emission rate is low, so the capacitance changed slowly, very slow. At high temperature, the capacitance changed very quick. If you have kind of observation window with T1 and T2, you can see the difference of this within this window, observation window. And you will get kind of curve like vertically like this. At low temperature, the signal, the DLTS signal is low, and the high temperature is also low. At a certain temperature, the emission or the DLTS signal will be very high. So we can modify these equations to, so this equation we talk about, we can modify this equation to here. So this signal we get from the DLTS measurement, and it depends on the temperature. If you can fit the value of this one, and we can get more information about the level, energy level of these trap states. So we can measure. This is a typical setup in my group. We use this DLTS to record to measure the deep states. And that's all for the characterization of semiconductors for both mobility and trap states. We can talk a little bit more about devices we have done. So if you have all the parameters like optical constants, you can use the N and K to do optical simulation of your real devices. Then we did some for perovskite solar cells in the beginning, and we also designed some concentrators for solar cells because the solar cells will normally work better under high light intensity. So we increase light intensity to like 10 cents, 100 cents, and the efficiency will go up because the open circuit voltage can easily go up. So these are all from the understanding of the charge transport. We also record transient emission of some perovskite-based devices. It seems highly dependent on the ion migration, because if you have slower ion migration, you will get a higher EL signal, and it's time resolved. We have done some thing about the light emitting property of perovskite devices as well, and also do some work on the ion migration. And more recently, we are working mainly on photodetectors. So we fabricated like 7 years ago the perovskite-based photodiodes, and we found the perovskite has very large dielectric constants. So the capacitance is very high. It resulted a very high or large RC time constants. So it limited the response speed of perovskite photodiodes a lot. Then we optimize devices with we want to reduce the device area and increase the active length or the thickness, and we reduce the RC, and we want to increase the bandwidth of the devices. And recently we reached around 20 nanosecond response. It's very fast. It's based on perovskites, and we also want to push it to like over gigahertz. So it's our aim, because from the charge transport, it do not have any problem. It has very high mobility. It should have very fast charge transport, and the devices should respond faster, but for real devices, we cannot get higher. It's mainly dependent on the device structure. And we also work on chalcogenides. So we work on antimony sulfides, bismuth sulfides, and we do a lot of measurements on the chalcogenides, and we want to increase the mobility of these films. If we have very high mobility, you will get a very fast charge transport, then you can get a high bandwidth photodiodes. So that's the aim for device optimization. And we also do some like color discrimination. And if you use like silicon photodiodes, it's a broadband semiconductor. No, it's a narrowband semiconductor. It has broadband photoresponse. So if you want to like detect red, blue, green individually, you have to use a lot of filters. So normally you use like a lot of filters, and the size of the silicon detectors nowadays are very small, normally around a few micrometer, and you have like 5 or 10 million pixels in an array. So you have to put a lot of the filters in front of the photodiodes, and if it should like have very good like matched fabrication. But if it's not matched very well, then you will lose your resolution a lot. So our idea is to reduce the usage of filters. How to design narrow band photodetectors. So we use perovskite early years because perovskite has tunable optical constants or optical absorption spectra. If you have high absorption coefficient at a low, a short wavelength, and you have very low absorption coefficient at a long wavelength region, the carrier generation will be quite different. For high alpha, you will get surface generation because most of the carriers can be absorbed just in front of the ITO electrode, not in front of the active layer. So it's very close to the ITO electrodes. If you have low alpha, then the light can penetrate much deeper. It generates carriers in the bulk. So the surface generated carriers takes longer distance to be collected, and the bulk generated carriers do need a shorter drift distance. So if you can tune the charge transport processes, you can selectively collect the bulk generated carriers, but I don't want to collect any surface generated carriers. Then you will get a photo response like this, the red dashed line. So you will not get any photo response from the high alpha region, and you can get relatively higher photocurrent from the long wavelength region, and you do not have any absorption after its absorption tail. If you can tune the absorption spectra, you can tune the photo response spectra of the devices. So this is the idea of our RGB devices, and we first achieved it based on the perovskite materials, and we got the 3 devices, and we compare the commercial photodiodes, and it has much better or sharper onsets. This is from Kodak, and this is our real devices. And recently we also realized real devices from chalcogenides. So we use different chalcogenides, and we achieved the tuning of absorption. And we also use these chalcogenides realized, and we did some characterization on the optical and electrical properties, and we do some optical simulation as well. And we also achieved a very narrow photo response from the chalcogenide semiconductors. So we fabricated 4 devices with very narrow EQE spectra, and you use it for imaging, and also they are fast. So these devices can have 240 nanosecond response, and we can use for optical communication as well. The other things we are doing in my group is the imaging. So we use perovskite single crystals, and we do some X-ray imaging in our work in my lab. And this is a single pixel device, and we just move the device X and Y, and we can scan the image. And the second method is to fabricate arrays. It's more easier, or technically it's more difficult, but it's for real application it's easier, I think. So we fabricate like more than 1,000 pixels in my lab, and we also do the imaging work as well. And we use some synthesizers and combine with a commercial CCD. We can also get very clear X-ray images from the perovskite scintillators. And recently we are working computation imaging. So we use single pixel photodetectors, and we modulate the light source, and we use the single and we record the photo current of the single pixel photodetector, and at different like modulation, and we do faster Fourier transform, and we can also get clear images from the modulation. And recently we also working on single photon detection systems, mainly used for gamma ray and neutron detection. And I want to summarize my talk. In this talk, I mainly introduce a lot of methods, transient methods, to characterize the charge transport of solution process semiconductors. And this is the main work we are working on, the TRMC, scientific EQE, and the DLTS. And we also do some device work, we do some optical modeling, and we do more work on photodetectors recently. And recently I also contributed a chapter of this book. If you are interested in all the details, you may have a look at this book as well. And I should thank my students for their hard working. And the group is growing up a little bit. In like 5 years ago, we only have like 5 students, and now I have more than 10. And I also thank my collaborators, and thank you for your attention. Thank you.
Thank you very much for the fantastic talk. I really enjoyed it. Actually, I don't have any questions. I had a list, but actually during your talk, you answered all of them.